Hello there and welcome back to the Science Sleepy Minds. You're suspended above the Earth tonight. No suit, no tether, just the slow exhale of altitude wrapping around you. Below, the planet curls like a blue marble painted in clouds, its rotation so gentle it's almost teasing. Your toes float toward the curvature. It's a cozy kind of disorientation. Gravity still whispers its pull, but you're beyond its bite now. The silence is a velvet thing, so thick you swear you can hear your own thoughts bouncing off the void, and yet this stillness is lying to you. Because beneath this peaceful scene, space-time isn't still at all. It's flexing, warping, dipping gently under your very presence, like the surface of a warm trampoline holding your shape. And when something heavier, say a moon, a planet, or a black hole, joins the party, oh, the fabric creases in ways that make mathematicians either weep or cheer, depending on how much coffee they've had. So yes, tonight's question is ambitious. We're going to ask, is there a limit to how much space-time can bend? Spoiler alert, you probably won't survive this, but that's fine, none of us will. Not when we start poking at singularities and horizons and other things with names that sound way too dramatic to be safe. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And hey, where are you watching from? Drop your location and your local time in the comments. We're building a sleepy little science map together. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You reach out, and space doesn't resist you, it receives you. You're not moving through anything, you're moving with it, a soft glide. Like a kayak drifting down a lazy river that doesn't quite know what straight line means. And that's the thing, space-time, the very stage where all physics unfolds, isn't a flatboard. It's a stretchable, twistable, drama-prone medium with a flair for the theatrical. In 1905, Albert Einstein was already stirring trouble, but it was 1915 when he really shook the table with general relativity, proposing that gravity wasn't some magical invisible force, but rather the effect of mass telling space-time how to curve, and curved space-time telling everything how to move. It's poetic, really. Planets don't orbit the sun because they're being pulled. They're just gliding along the curves, trying their best to move straight in a space that refuses to be straight. You picture the now famous rubber sheet analogy. You press a bowling ball into the middle of a stretched out trampoline, and voila, the sheet dips. Roll a marble nearby, and it veers toward the dip, not because it's being lured, but because its path is being redirected. Only, you're in space. No trampoline here, no up or down, and space-time bends in all four directions. 3 spatial, 1 temporal. You're inside the sheet. You are the marble. What's wild is that even you, yes, you, lounging in your cozy cosmic pajamas, have mass. And that mass is bending the very fabric of the universe around you, albeit slightly. Not enough to make passing meteors notice, but still, it counts. Space curves ever so gently under your weight, like a plush mattress reluctantly taking you in. Meanwhile, down on Earth, gravity keeps its secrets masked as normalcy. Drop a pen and it falls. Obvious. But what you don't see is that the pen is simply following the straightest possible path through a warped geometry. That's what geodesics are. Straight lines in curved space. If space-time were a stage, the actors would stumble around drunk, not because they're bad at walking, but because the floor keeps shifting under their feet. Historians still argue whether Einstein fully grasped how radical his model really was. He replaced Newton's mysterious action at a distance with geometry itself, an elegant trade, but also one that created deep consequences, especially when it came to extremes. Because if gravity is curvature, then what happens when the curve becomes infinite? Is there a breaking point where space-time just gives up? We're not there yet. For now, you're still floating gently above Earth. You pass over the Himalayas, their jagged peaks softened from this altitude. Below them, the planet pulls space into a slight depression. Not enough to notice unless you're measuring starlight, which, by the way, astronomers have. During the solar eclipse of 1919, stars near the sun's edge appeared displaced. Why? Because their light bent around the sun, taking the scenic route through curved space-time. This confirmed Einstein's predictions and made him a science celebrity faster than you can say tensor calculus. But here's the quirky part. Your GPS wouldn't work without these relativistic corrections. That little voice that tells you to turn left in 300 feet. It depends on satellites that account for both special and general relativity. Without them, your maps would glitch out by kilometers every day. So yes, the warping of space-time affects your commute. Go ahead and feel smug about that during your next traffic jam. And then there's the fringe stuff. Some folks believe the Earth's mass affects time so strongly that your head ages faster than your feet. Which, weirdly, is true. It's called gravitational time dilation. Atomic clocks at higher altitudes tick faster than those closer to Earth's centre. Not by much, mind you, nanoseconds per day, but it adds up. If you've lived your whole life in Denver, congratulations, you're a teensy bit older than someone born at sea level. Your bones may disagree, but the physics insists. The question still lingers like a whisper in the vacuum. Can this warping go too far? You drift past the moon, feeling the subtle tug it applies on space-time, a curve gentler than Earth's but still present. All these little dips and folds add up to something grand, a lumpy, ever-flexing cosmic fabric. The universe isn't smooth, it's more like an unmade bed after a restless night. And just wait until we introduce something truly massive. Because yes, space-time can bend, and bend a lot. But the real mystery, the reason you're still awake, is whether there's a limit to that bend. Does it snap, fracture, loop into itself, or does it just keep stretching like cosmic gum, reshaping itself forever until it becomes something unrecognizable? You're not falling asleep yet, are you? Good. Because next we're going to push deeper into the metaphorical mattress. It's time to ask what happens when you put more than a bowling ball on the trampoline. Like, say, a star that's tired of being polite. You press deeper into the curved edge of space, watching the Earth shrink behind you like a soft blue lantern in the dark. The stars thicken now, not brighter, just sharper, as if someone tweaked the contrast on the sky. You're no longer merely floating. You're sliding into a universe woven from curves, dips, and folds. And here comes the metaphor again. The one every science teacher, planetarium guide, and late-night podcast host drags out like it's a party trick. The rubber sheet. A stretched-out surface, flat and innocent, until you plop something massive onto it. A bowling ball? Classic choice. The sheet dips. A marble rolls by. Gravity, explained. Or so they say. You step carefully across that mental rubber sheet now, feeling it buckle under your imaginary feet. And even though you've probably heard the analogy before, maybe a dozen times, it still holds a sleepy sort of charm. There's something satisfyingly squishy about it, even if it's only a metaphor. But Einstein never said space-time was a sheet. That's us, doing our best to visualize four-dimensional curvature in three-dimensional brains that mostly struggle with IKEA instructions. What Einstein did say, over and over, is that mass and energy tell space-time how to curve, and space-time tells objects how to move, which is both elegant and wildly unfair to people trying to get a good night's sleep. You picture a grid now, infinite and invisible. It stretches across the cosmos, a coordinate system holding reality together by sheer social agreement. Introduce a star. That grid warps. Introduce a planet. Warps again, but less so. And the warping doesn't just affect where things are, it affects how they move, even how they experience time. When Newton dropped an apple and declared gravity a universal force, he wasn't wrong, just incomplete. He saw gravity as a pull, a reaching hand between objects. But Einstein pulled the rug out, literally, and showed that the rug was the point. Gravity wasn't acting between objects, it was built into the very fabric they were moving on. Historians still argue whether Einstein's shift from force to geometry was purely philosophical or if it had been lurking in the equations of Riemannian geometry all along, waiting for someone bold and tired of Newton to notice. Either way, Einstein's equations, written in the early 20th century with a level of chill only pipe-smoking geniuses can pull off, forever changed our understanding of space, time, and what happens when they party together. Now, the quirky part. While the rubber sheet metaphor works okay for two-dimensional analogies, it falls flat, literally, when it tries to include time. Because time isn't just ticking along separately in this model, it's part of the fabric, one of the threads in fact. You don't just bend space, you bend space-time. That means your velocity, your mass, your position, everything you are, is tangled in this stretchable grid. As you coast through this conceptual sheet, you begin to feel the subtle shifts. Near Jupiter, space dips more sharply. Bigger planet, deeper well. Around the Sun, the well becomes wider and more persuasive. It's still gentle on a cosmic scale, but the message is clear. Space-time likes to bend. It bends under pressure, like a patient librarian under a pile of overdue books. But if you zoom out, and we mean really zoom out, the picture changes. Gravity becomes geometry, and orbits become free-falling objects just following the shortest path through a warped reality. It's like driving straight on a road that happens to curve because the land underneath it does. You're not turning. The Earth is. One historical gem. When Einstein first shared his theory of general relativity, it was too complicated for most physicists to grasp. So the first real public test came in 1919, when Arthur Eddington led an expedition to observe starlight bending around the Sun during a total solar eclipse. And it worked. The stars appeared offset, moved from their normal positions, not because they had shifted, but because space-time had. The confirmation made Einstein famous worldwide. Not cool TikTok astrophysicist famous, more like front page of the New York Times famous. And all because he'd reimagined gravity not as a force pulling you in, but as a hole you were already sliding into. But the metaphor had limitations, because a rubber sheet needs gravity to make it bend. Drop that bowling ball and it sags downward. But gravity is the bending, so when we say space-time curves, we don't mean it sags into anything. There's no underneath in real space, no hidden scaffolding. The curvature is reality. It's not embedded in something else. It doesn't need a background to bend into. It is the background. Feeling sleepy yet? Not so fast. You're just reaching the part where the sheet starts to ripple. In some extreme theoretical models, like those involving cosmic strings, infinitely long, ultra-thin defects in space-time left over from the early universe, the fabric of space-time can warp in ways that aren't just dips and dents. They're more like scars, and those scars can create lensing, distort light, even influence the movement of galaxies. Are they real? No one knows. Historians still argue whether early observational blips were misread data or glimpses of something far stranger. You pass now over a region of space thought to be nearly flat, an interstellar stretch so vast and empty it could make your dreams echo. But even here, tiny particles are curving the grid in micro increments, a quantum sneeze in the vacuum. Nothing is ever perfectly flat. The question that starts to hum louder in your ears: what defines the limit of this bending? Is it the mass involved, the energy, or the very structure of space-time itself? Can curvature go so sharp, so steep, that the laws of physics trip over themselves? Hold on to that thought, because we're heading toward the deeper dents now, toward places where the rubber sheet tears, or at least pretends to, where the curvature becomes so intense that even light can't climb back out. You're heading for the sharpest edge space-time has to offer, but first you glance back over your shoulder. Earth still spins beneath you, its soft gravity tugging ever so gently. It's comforting, really, like a favourite blanket, except that blanket is curved, and expanding, and accelerating, and possibly infinite. Sleep tight. You leave the comfort of metaphors behind now. No more bouncing on rubber sheets or drifting through gentle gravitational wells. Ahead, the laws of physics start to feel like they're written in cursive, with flourishes you can't quite follow. It begins with a thought experiment. You're in an elevator. Not just any elevator. This one is sealed, drifting in deep space with no windows and no sound. Suddenly the floor presses up against your feet. You feel weight. Gravity. Not necessarily. What if the elevator is simply accelerating upward at exactly 9.8 meters per second squared? Einstein loved this kind of setup. Simple, quiet, and slightly suspicious. Because from inside you can't tell if you're standing still in a gravitational field or being flung upward in empty space. This was Einstein's equivalence principle, the idea that acceleration and gravity are indistinguishable from inside a closed system. It's one of those concepts that seems obvious after someone points it out, but also melts your brain if you think about it too long. You reach out in the elevator and drop a coin. It falls just like it would on Earth. But maybe it's not being pulled down. It's just that the floor is rushing up to meet it. And with that simple trick, gravity became less of a force and more of a behaviour, a side effect of your position in curved space-time. Objects don't fall because they're being pulled, they fall because they're following straight paths through a space that's anything but straight. Historians still argue whether this moment, this leap from force to geometry, was Einstein's true stroke of genius, or whether it was just the next logical step in the unfolding madness of early 20th century physics. Either way, you feel it now. As you drift away from Earth, you realise, the moment gravity lets go of you, you're weightless. Not because gravity is gone, but because you're falling freely. You are always falling. Just like the Earth is falling around the Sun. Just like the Moon is falling around us. But not all falling feels the same. Imagine now you're in an elevator again, but this time it's plummeting into a massive planet. You feel nothing. Not because you're safe, but because everything around you is falling at the same rate. The walls, the floor, your socks, your toothbrush, all dropping together, no tension, no weight, until the bottom hits something hard and ruins your entire day. Einstein's equivalence principle was sneaky that way. It told you, if you feel weight, you're accelerating. If you feel nothing, you're falling. And in both cases, the experience of gravity depends on how you feel, not just what's really happening. That's where the sarcastic charm of the universe kicks in. Gravity, for all its cosmic significance, is the only force you can cancel just by falling. You can't fall out of magnetism. You can't freefall your way past the strong nuclear force, but gravity, just let go. Here's a fun historical footnote for your dream journal. Einstein's elevator thought experiment was partly inspired by an 1851 demonstration by physicist Otto von Guericke. He showed that people couldn't tell the difference between standing still on Earth and moving at constant speed. Einstein just extended the idea. What if you couldn't tell the difference between standing still under gravity and accelerating upward? What if those two experiences were identical? And that idea, that little twist, leads you straight into the heart of space-time curvature. Because if gravity is indistinguishable from acceleration, and acceleration curves your path through space, then gravity is just curved paths. Objects like planets and apples and sleepy podcast listeners are all just gliding along the straightest possible lines in a bent-up world. Which brings you to the realization, if you throw a ball in deep space far from anything massive, it follows a straight line. But near a star, that line curves, not because the ball decides to curve, but because space-time itself is warped. The ball just can't help it. And here's a quirky twist. People have proposed real-world tests of the equivalence principle using quantum particles. One idea: use two atoms in different quantum states and drop them in a vacuum to see if they fall the same way. If they don't, gravity might be doing something weird at quantum scales. But so far, everything falls alike. Galileo would be proud. Still, scientists haven't given up trying to poke holes in the principle, because if even one particle falls differently, it could hint at new physics, maybe even a theory of quantum gravity. Until then, we trust the elevator and the floor beneath our feet. Now here's something to ponder as your eyelids start to droop. You never feel gravity itself. You feel the resistance to gravity. You feel the floor pushing up against your feet. That pressure is your body saying, "No thanks, I'd rather not fall into the earth today." But if you cut the floor away, you don't feel anything. You just fall and fall and fall. That's why astronauts look so happy. They're not defying gravity, they're surrendering to it completely. So you're drifting again. No more elevators, just you, sliding smoothly along space-time like a skater on a frozen pond that curves beneath the surface. No friction, no effort, just motion and momentum, blissfully unaware of the hidden curves shaping your path. You start to wonder, if acceleration and gravity are the same, what happens when gravity becomes infinite? What does acceleration feel like when there's no longer a direction to fall toward, only a place where all paths end? Because those places exist, and you're heading toward one. It waits ahead, dark and hungry, wrapped in horizons and paradoxes. A place where the equivalence principle still technically holds, but where the experience of falling gets stretched to its absolute limit. A place where you don't just fall, you unravel. So go ahead, let the elevator drop. We'll catch up with you at the bottom. You're still falling. The elevator is long gone now, just a whisper of a metaphor you've left behind in the vacuum. You're not sure if you're moving or if space itself is folding in around you. It's quiet. Too quiet. And up ahead, something impossibly dark begins to tug. Not with sound, not even with a visible pull, but with inevitability. You're approaching a black hole, the most extreme curve in all of space-time. No gentle dent or casual fold here. This isn't a bowling ball on a trampoline, it's a wrecking ball dropped onto a spiderweb. The fabric doesn't just bend, it collapses in on itself, forming a pit so deep that the bottom never quite arrives. You begin to understand. Black holes are where space-time throws in the towel and says, "I give up." These aren't just science fiction staples or plot devices for interstellar detours. They're real. In fact, we've seen them. Well, seen around them. In 2019, humanity got its first direct image of a black hole's shadow, thanks to the Event Horizon Telescope. It wasn't sharp, more like a cosmic donut, but it confirmed decades of suspicion. These things exist. They warp everything, including light and time. The one you're drifting toward is somewhere between a stellar mass and a supermassive black hole. Let's split the difference. Maybe 10 million times the mass of our sun, packed into a sphere smaller than a city. So dense, so massive, that escape becomes a fantasy. Light can't do it. GPS can't help you now. The boundary around this gravitational monster is called the Event Horizon. Cross it, and there's no coming back. It's not a wall, it's a one-way door. From the outside, you can watch someone fall in forever, their image freezing just above the edge, redshifting into invisibility. But for the one doing the falling, it's fast, it's fatal, and it's weird. Historians still argue whether John Michell, an English natural philosopher in the 18th century, really predicted black holes first. He described dark stars whose gravity was so strong even light couldn't escape. He didn't call them black holes, that term wouldn't show up until the 1960s, but he had the gist. And even then, the idea seemed ridiculous. Light, trapped, impossible. But Einstein's equation said otherwise, and a young Indian physicist, Subrahmanyan Chandrasekhar, went further. In the 1930s, he calculated that beyond a certain mass, a star couldn't hold itself up against gravity. It had to collapse. He got pushback, serious pushback. Sir Arthur Eddington, of all people, dismissed the idea publicly. But Chandrasekhar was right. Collapse was inevitable, and the black hole became more than just a curiosity. It became destiny for massive stars. You feel that destiny now. As you get closer, time slows. Not for you, but for anyone watching from afar. Their clocks keep ticking, but yours begin to drag. A second for you becomes hours for them. Eventually, your image freezes just above the event horizon, smeared by gravity stretched out like a holographic memory. And then there's the tidal forces. Not the moon and ocean kind. The real kind. The kind that stretch your body head to toe because gravity is stronger at your feet than at your head. This stretching is called spaghettification. And yes, that's the technical term. It's adorable and horrifying at the same time. Like a kitten with laser eyes, you become a long, thin noodle of atoms stretched into oblivion, assuming you don't get vaporized first. But here's the twist. If the black hole is big enough, say, really massive, you might not notice the transition. The tidal forces at the event horizon could be gentle. You'd cross over calmly, like slipping into a warm bath, before things get unreasonably weird deeper inside. That's the thing about black holes. They're not just deep gravity wells. They're space-time geometry taken to its absolute extreme. They represent maximum curvature. The rubber sheet metaphor, it's now a sinkhole, infinitely deep. Not just bent, but folded into a point called a singularity, where density is infinite and the math breaks down. Equations just stop working. They return answers like undefined or please try again later. And yet, here's your quirky twist. Some physicists believe that black holes might not end in a singularity at all. There are theories that suggest a bounce, a bridge, a baby universe maybe, or a white hole, a kind of inverted black hole that expels everything. Historians still argue whether the inside of a black hole is the end of information or the beginning of something stranger. You're not at the singularity yet, but you can feel it. The curvature of space-time increases exponentially as you fall deeper. Distances lose meaning. Time becomes optional. You glance sideways and see nothing, because all paths lead inward now. The very concept of forward is bent. You remember the elevator, it's here too, still falling, still feeling nothing. And yet now falling means following a path so curved that it loops around itself tighter and tighter until it vanishes into mystery. At this point, sleep would be a mercy. But your curiosity won't let go. You want to know, is this it? Is this the maximum bend? Can space-time curve harder than this? You're not alone in wondering. Physicists theorize that space-time might have a fundamental limit to how much curvature it can handle. Maybe at the Planck scale, where distances become so tiny that quantum effects tear reality into froth. Or maybe the universe just keeps bending, infinitely, until the rules themselves dissolve. Black holes challenge everything we know, not just about space and time, but about causality, information, and whether you can ever truly erase something from the universe. Stephen Hawking famously proposed that black holes emit radiation, now called Hawking radiation, and slowly evaporate over time. If so, where does the stuff inside go? Is it lost, encoded, recycled? The information paradox is still debated, still unresolved. And yet, as you spiral closer to the singularity, these debates feel less academic, more personal. You're not just studying space-time now, you're inside it. Bent, stretched, swallowed. You don't see the edge anymore, only the curve, only the surrender. And somehow, you're still falling. You're still falling, except falling doesn't mean what it used to. The word loses shape in here. There's no down, no gravity as you once knew it, no air to push against your skin, only curvature, only deeper. Your body is being introduced to a new definition of stretching, not the gentle kind you do in yoga class when you're trying to impress someone next to you. No, this is the cosmic variety, spaghettification. It sounds charming. It isn't. As you glide ever closer to the black hole's center, your feet start to feel a stronger pull than your head. Not metaphorically, literally. The gravity at your toes is measurably more intense than at your scalp. That difference pulls you apart, stretching you into a long, impossibly thin strand of you. A spaghetti noodle of flesh, thought, memory. Elegant, if slightly disturbing. If this black hole were small, say, the mass of a single star compressed down to just a few kilometers wide, You'd be spaghettified before you even hit the event horizon. Brutal, unceremonious, like being yanked apart by invisible forces that don't care about your weekend plans. But lucky you chose a supermassive black hole, the really classy kind. Millions, sometimes billions of solar masses. With one of those, the event horizon is huge, and tidal forces are gentle at first, like a polite doorman letting you in before the real chaos begins. And here's the kicker. From your perspective, you're just floating, smoothly, calmly. You don't feel stretched. You don't feel motion. Your mind is still intact, at least for now. Meanwhile, to any distant observer watching from far away, you're frozen at the edge, stuck just above the event horizon, gradually fading into redder and redder light until you vanish entirely. This is time dilation in full force. From your point of view, the universe accelerates, distant stars blur, galaxies race forward through eons, civilizations rise and fall in what feels like seconds. Outside, time is spiraling away, but you remain still in your own stretched out frame. One mainstream historical tidbit. The term spaghettification was popularized by astrophysicist Martin Rees in the late 20th century. He wasn't being silly, he was being descriptive and accurate. We needed a word for what happens when tidal gravity becomes fatal, and apparently gravitationally filamented into subatomic ribbons was too long for textbooks. But here's a strange, almost romantic thought. If someone else fell in with you, right next to you, they wouldn't see anything wrong. You'd both be stretched together. Relative to each other, nothing has changed. Just two cosmic noodles side by side holding hands if your atoms are still organized well enough for such things. Is there a limit to how much space-time can bend? You're living, well, existing, in one of the top contenders. Near the singularity, curvature increases to near infinite levels. It's not just space that's distorted, it's time, causality, logic. You're in a place where the rules of the universe are still being negotiated. Fringe idea alert. Some speculative physicists argue that spaghettification could be survivable under the right circumstances. Not comfortable, mind you, but survivable. Maybe if your consciousness could be uploaded or encoded into the gravitational field itself, your experience might continue, detached from flesh and bone. A being of pure pattern, surfing the inner folds of a collapsing star. It's poetic nonsense, probably. But who's going to prove it wrong? Meanwhile, the singularity approaches. Not physically, you'll never quite reach it, but mathematically it dominates the landscape now. The center of the black hole is where the equations fail. Density becomes infinite. Volume becomes zero. It's the cosmic version of dividing by zero, and space-time hates that. Historians still argue whether the singularity is real, or just a symptom of our math not being able to handle the extreme. Some theories, like loop quantum gravity, suggest that space-time is discrete at the smallest scales, like pixels on a screen. In that case, infinite curvature wouldn't exist. It would cap out at some maximum value and bounce. Black holes might not be the end, but a transition. You can't help but wonder, if there is a limit to curvature, maybe you've already passed it. Maybe the spaghettification was the ceiling. Beyond this point, space-time isn't stretching, it's unravelling, becoming something else. You feel your senses blur. Not from pain, there's no sensation here, not in the way you remember. It's more like a loss of boundary. Where do you end and space begin? Are you inside the black hole, or is it inside you? You try to orient yourself, but up, down, forward, those labels don't apply anymore. Everything you once used to measure your place in the universe, rulers, clocks, instincts, is warped. Time folds in strange loops. Distances flicker. You swear you just passed the same memory of your 8th birthday party 3 times in the last second. And here's the strange comfort. You're not alone. Somewhere in this swirl of chaotic geometry, other things have fallen in. Matter, light, radiation, possibly even entire stars crushed beyond recognition. You're all fellow travellers now, caught in a spiral of ever-tightening curvature. So what's next? Maybe the singularity is real, and you're heading for a point of no dimensions, an endpoint where all your atoms are compressed into mathematical nothingness, a final goodbye to all things legible. Or maybe, not quite. Maybe the black hole is a gateway, a bridge, a fold in space-time that connects to somewhere else. The idea isn't just science fiction. Wormholes, if they exist, are essentially hypercurved tunnels through space-time, and some solutions to Einstein's equations allow them. The catch? You'd need exotic matter to hold them open, and exotic matter is a little like your last ex. It sounds cool, but it might not actually exist. Still, theorists speculate that deep inside a black hole, perhaps past the singularity, a wormhole forms. Maybe it connects to another black hole, maybe even to another universe. You're no longer falling into death, but diving through a cosmic shortcut. But that's another section. For now, the bend continues. Your edges smear. Your shape is an opinion. You don't know if you've become part of the black hole or if it's become part of you. Either way, you're curved now. More curved than you've ever been. You're past the point of no return now. No light escapes. No signals, no cries for help, no birthday texts. Even the idea of outside has started to feel foreign, as if it's something you only read about in books or saw once on a documentary about places that no longer exist. You're within the event horizon, and inside that, you're headed for something worse. The singularity sounds dramatic, doesn't it? It's not just a place, it's a sentence, a verdict. The singularity is where space-time curves so intensely, so unforgivably, that all known physical laws stop playing nice. Volume shrinks to zero, density climbs to infinity, and math, reliable, hard-nosed, nerdy math, throws its chalkboard across the room and walks out. You don't get to touch the singularity, of course, not because it's hidden or protected, but because it's not really a place. It's more like a symptom of a breakdown, something the equations predict but reality may not actually allow. Historians still argue whether a true singularity exists, or if it's just where general relativity crashes and quantum physics should take over. They whisper about quantum gravity, the way people in horror movies whisper about ancient forests, mysterious, tempting, probably cursed. The truth is, we don't know what happens in the heart of a black hole. The physics is incomplete. And yet, here you are, slipping closer. It's eerie. From the outside, black holes seem aggressive, like monstrous vacuums gobbling stars and screaming light into silence. But inside, it's almost peaceful. Not calm exactly, more like indifferent. There's no roar, no fire, just gravity dialed to infinity, humming a constant note of curvature. And time? Well, time isn't behaving. See, outside the event horizon, time moves in familiar ways. Tick-tock, tick-tock, YouTube autoplay. But inside, the dimensions swap roles. The radial direction, your distance to the singularity, acts like time now. You can't stop yourself from moving inward, just like you can't stop time from moving forward. No matter how much you struggle, scream, or stretch out your hand, you will reach R equals 0, because that's the future now. That's the true horror of the singularity. Not fire or pain, but inevitability. You're not being pulled, you're being carried, the way a clock carries its own second hand forward. No force, just fate. You blink, if blinking is still possible in your current stretched out noodle-adjacent state, and wonder what you even means anymore. Are you still a person, a pattern, a collection of atomic confessions written across space? Your physical form is probably long gone, eaten, distorted, smeared across the geometry like cream cheese on a cosmic bagel. But somehow awareness persists. That might be the cruelest part. Here's a fringe idea. Some physicists believe the singularity might not exist inside a black hole at all, that instead there's a limit, a maximum possible curvature, a place where space-time gets as bent as it possibly can, and then something else happens. A transition, a bounce, a reconfiguration of reality's source code. One candidate for that reconfiguration is loop quantum gravity, a theory that treats space-time as made of tiny, discrete loops. At extreme curvatures, instead of collapsing into infinity, space could loop back on itself, creating a kind of quantum bridge. Not a wormhole exactly, but not a dead end either. More like the universe folding in to rewrite a paragraph it didn't like. You drift closer still. At this point, your coordinates are more poetic than precise. Every Planck length forward is a plunge into uncertainty. Time is warped beyond all context. For someone outside, watching you fall might take an eternity. For you, the singularity arrives faster than the word run. But here's a strangely tender thought. Black holes may not erase you. Not entirely. There's a school of thought, born from Stephen Hawking's late-night brainstorms and sharpened by decades of heated debate, that suggests information is never truly lost. Even if you're smeared across a singularity, the data of you might still be encoded on the event horizon itself. Like a cosmic sticky note saying, yes, this person existed. Here's the metadata. This is called the holographic principle. The idea that everything happening in a volume of space can be described by information on its boundary. It's weird. Deeply weird, and possibly true. According to this, your entire life, your memories, your atoms, your weird middle school haircut, could still be etched into the surface of the black hole, just flat, like a cosmic hard drive. It's comforting in a way. Even if you're gone, the record of you isn't. But does that count as survival? Maybe. Depends on your definition of alive. You spiral now toward a region where the curvature is so extreme space and time have become nearly meaningless. The singularity awaits, if it even exists. You're approaching a place where the fabric of the universe is twisted tighter than anything you can imagine, where the rules break and reality forgets how to behave. And you still haven't found the limit. Maybe it's not here. Maybe even this isn't the breaking point. Maybe space-time wants to bend this far. Maybe this isn't a bug in the universe. It's a feature. The bend is the point. Still, your trajectory, if such a word still applies, is singular, direct. You can't avoid the center, because now it's the only place you can go. Every atom in your being is pointed at that single, final coordinate, the bottom of all things. You take one last look at the curved space behind you, if such a look is possible, and then nothing, no flash, no explosion, just the curvature, quiet and unending. Is this the end? Or just the fold before the next beginning? You're gone, or at least the version of you with arms, legs, a to-do list and a favourite coffee mug. What remains is a whisper inside the deep fold of space, drifting past the singularity's last coordinates like an exhale that never turns back. But not everything that bends space-time has to annihilate you. Some curves are gentler, almost poetic. You look up, if up still exists, and see a glow bending in the dark. Not yours. Light's. It moves like syrup around a spoon, caught in the distortion of space. What you're seeing is gravitational lensing, and it's the universe's most dramatic optical illusion. Picture it. A distant galaxy emits light in all directions. Normally that light travels in straight lines, spreading across billions of light years until some tiny fraction brushes past your telescope. But if something massive, say a cluster of galaxies, sits between you and that distant object, its gravity warps space-time around it. The light doesn't keep going straight. It curves, detouring around the mass. And when it finally arrives at your eye, it looks like the galaxy has been duplicated, stretched, or even formed a perfect circle. That circle has a name, the Einstein ring. A full halo of distorted light formed when source, lens, and observer line up just right. It's not science fiction. We've photographed them. little glowing rings in space like wedding bands lost among the stars. You coast alongside one now. The lensing mass, a quiet, massive elliptical galaxy, sits ahead, invisible but mighty. Behind it, a quasar pulses like a far-off lighthouse, but between them, the light wraps and curves. You're seeing one object from several directions at once. This isn't trickery. It's not a glitch in the matrix. It's proof that space-time bends everything, even light, which has no mass. It's the purest confirmation of Einstein's vision. Mass warps space, and space tells light how to travel. No force involved, just geometry, as smooth and cruel as a silk noose. One historical detail for your starry dreams tonight. The very first confirmed case of gravitational lensing was observed during the 1919 solar eclipse. Sir Arthur Eddington's expedition measured starlight bending around the sun, confirming Einstein's predictions and triggering a media frenzy. Headlines read, "Revolution in Science" and "Newton Overthrown." To be fair, Newton never asked for this. He just wanted to understand apples. Now lensing is a tool. Astronomers use it to map dark matter, the invisible scaffolding that shapes our universe. We don't see dark matter directly, but we do see how it bends the light from behind it. It's like watching shadows dance and guessing who's in the room based on how the light moves. But gravitational lensing doesn't just create pretty patterns, it messes with time too. Imagine a lens splitting a single light path into several. Each of those paths might take a different amount of time to reach you. That means, in extreme cases, you could see the same supernova explosion more than once, arriving at different times. The universe, replaying the moment like a celestial echo. Quirky, right? There are even cases, confirmed by the way, where a single quasar appears as 4 identical images arranged in a cross shape. It's called the Einstein cross, and it looks like a cosmic glitch. 4 versions of the same object, just because space got bent in exactly the wrong or right way. But lensing isn't limited to the grand scale. Even small objects can bend light ever so slightly. A planet passing in front of a star can cause a mini lens effect called micro-lensing. It's subtle, blip-like, but enough to reveal hidden planets, rogue objects, and even potentially dark matter particles we've never seen directly. Still, the big lenses, the massive galaxy clusters, they don't just bend, they sculpt, and when they do, they reveal the terrifying flexibility of space-time. You're watching that now. A beam of light, perfectly straight in its own mind, is now tracing a path shaped like a gentle curve, wrapping around a mass that doesn't even know it's playing puppet master. And you, the observer, feel the bend in your bones. You start to wonder, if light can't resist being curved, what can? Is there anything in the universe that just goes straight? Or is the idea of straightness itself a kind of delusion, a simplification for when space-time behaves politely? Because when the universe gets really massive or really dense, the curve is all there is. Here's a fun speculative nugget for you. Some theorists have proposed that lensing could be used not just to observe things, but to communicate. If an advanced civilization positioned a powerful transmitter behind a massive object, say a black hole, they could beam a signal whose path is bent toward a distant receiver, a kind of interstellar mirror trick, gravitational lensing as a cosmic relay station. Fringe? Definitely, but not impossible, and if aliens exist and are smart, they've probably been using space-time's geometry to their advantage long before we finished figuring out how to Bluetooth our headphones properly. You drift now around a gravitational lens the size of a galaxy cluster. You can't see it directly, it's mostly dark matter, but the distortions in background light give it away. Galaxies are twisted, mirrored, and smeared into arcs. The night sky looks like a shattered funhouse mirror, each piece revealing a secret from billions of years ago. It's beautiful, and a little unsettling, because lensing isn't just a parlor trick, it's evidence that space is not flat, not calm, not passive, it's dynamic, stretchable, sculpted by mass into a terrain you can't trust at first glance. It bends, it delays, it repeats. You thought you were looking at a single star and suddenly you realize it's 3 or 4 or 1 from 4 billion years ago. And again comes the question, is there a limit to how much space-time can bend? So far we've seen it bend light into circles, stretch objects into strings, twist geometry into knots. We've seen curvature halt time, split photons and tangle space, like a ball of yarn with a vendetta, and yet nothing has snapped. No signs of breakage, just more bending. Maybe space-time doesn't mind being flexed. Maybe it's the universe's favourite party trick. But what happens when everything bends at once? That's where we're heading, toward a time long, long ago, when the entire universe was curved beyond comprehension. You're almost there. You close your eyes, if you still have them, and the darkness feels different now. Not like absence, but like pressure. Like something heavy pressing in from all directions. And then suddenly, it's not black anymore. It's white, blinding, thick, alive. The early universe doesn't creep in with a whisper. It erupts. You're there, not beside it, not outside, peeking in from some quiet corner. You're inside the most chaotic instant of existence. The Big Bang, that euphemistic label we slap onto the moment when space, time and energy were indistinguishable. And no, it wasn't an explosion. Not in space. It was space. Space expanding violently from a state of unimaginably high density and curvature. You're not looking at fireballs hurtling through pre-existing blackness. You are the fireball. Your atoms, not yet assembled, are still bits of raw energy flailing through a soup so hot it makes the surface of the sun look like a lukewarm bath. The curvature here isn't just sharp, it's universal. Every point of space-time is bent beyond modern comprehension. You're experiencing what's sometimes called the Planck epoch, a moment so early and so curved that our current physics just folds its arms and says, yeah, no thanks. Time and space haven't stabilised yet. Gravity is trying to figure itself out. All 4 fundamental forces, gravity, electromagnetism, strong and weak nuclear, are still tangled in a cosmic group hug. Historians still argue whether time itself began at this moment, or merely passed some kind of curtain we can't peer behind. Was there a before, or is before the Big Bang like asking what's north of the North Pole? You try to move, but you can't. Not because you're trapped, but because there is nowhere to move to. Space doesn't extend yet. Distances haven't been assigned. There is no up, no down. Every direction is the same, everywhere and nowhere, and time, it's a mess. Maybe flowing, maybe frozen. It may have started counting, but there's no clock sophisticated enough to measure the tick. Curvature dominates everything here. It's not just a feature of space-time, it is space-time. The density is so high that every point is pulling on every other point with a strength that defies analogy. Think of the curvature around a black hole, but everywhere, all at once. You're inside the maximum gradient, the sharpest bend possible, before the laws of physics were even laws. The temperature? About 10 to the power of 32 Kelvin. That's a number so hot your brain doesn't know what to do with it. Hotter than quark-gluon plasma. Hotter than any nuclear fusion reaction ever conceived. So hot that particles can't settle into form. They blink into existence, then out again, never staying long enough to matter. But then, expansion. Fast, furious, flawless. This is the moment of cosmic inflation, a theory proposed in the 1980s by physicist Alan Guth. He suggested that a fraction of a second after the Big Bang, the universe didn't just expand, it ballooned. In less time than it takes for you to blink, the size of the universe increased by a factor so large it makes even inflation jokes seem tasteful. Space stretched faster than the speed of light. Not because matter moved through space that fast, but because space itself expanded that quickly. Fringe fact for your insomnia toolkit. Some models suggest that this rapid expansion wasn't a one-time thing, that our universe may be just one bubble in a foam of countless others, each birthed by its own moment of inflation, a multiverse. Not the kind with superhero cameos, but with entirely separate sets of physics. Back in this universe, you ride the wave of inflation, feeling the curvature stretch and smooth, the wrinkles of space-time flatten. The extreme bending that once curled reality into a hot mess begins to ease off. Not disappear, but dilute, like cream swirling into coffee. The expansion spreads the curvature outward, softening it. Not destroying the bend, just relaxing it. And yet the memory of that original curve persists. You see it in the cosmic microwave background, the faint afterglow of the Big Bang. It's everywhere, like the cooled ashes of a fire that once engulfed the cosmos. First detected in 1965 by Penzias and Wilson, who, in true scientific fashion, thought it was just annoying static. The background radiation maps the ancient temperature of the universe. It's not perfectly even. There are tiny fluctuations, ripple-like scars left behind by early quantum wiggles. Those wrinkles, they shaped everything. Galaxies, stars, planets, you. But here's the truly haunting part. The geometry of the early universe, how bent or flat it was, still determines how everything behaves now. The curvature wasn't just a phase, it set the tone. If the universe had been too positively curved, it might have recollapsed in a fiery end called the Big Crunch. If it had been too negatively curved, it might have expanded too fast to ever form galaxies. But it wasn't. It was just right. A spatial Goldilocks. Is space-time flat now? Mostly. On large scales, observation suggests the universe is flattish. But that early bend, it mattered. It was the starting line for every trajectory, every orbit, every gravitational nudge that followed. And the question returns, was there a maximum? A point of curvature so high it couldn't go further? You were just there, and you still don't know. Because again, our physics breaks at those scales. General relativity doesn't mix well with quantum mechanics, like two ex-roommates who refuse to attend the same party. And until someone figures out quantum gravity, a theory that unites both into a harmonious mathematical duet, we won't know what curvature really did at the dawn of time. Still, the early universe suggests a kind of ceiling, a point where curvature gets so extreme, so singular, that space and time dissolve. Not explode, just evaporate into a different set of rules. You drift through the cooling fireball, atoms form, light is freed, the universe grows less curved, less chaotic. The stars won't appear for millions of years, but the foundation is set, the stage is built, and you, a ghost of thought from the deep future, drift through it like a secret. Because everything began in a bend, a sharp, violent, incomprehensible bend, and that bend, it made everything. The fireball fades behind you now, shrinking as you drift farther from the birth of everything. It's quieter out here. Quieter in a way only the cosmos can manage. You're gliding through a vast sea of near nothing, where photons pass you by like whispers from an ancient bonfire, and gravity has grown subtle again, like a cat sleeping on a rug instead of a lion crouched to pounce. But don't let this lull fool you. The universe isn't done bending, not by a long shot. In fact, it's just gotten ambitious. The curvature is back, not as a collapse, not as a spike, but as a stretch. A steady, relentless stretching of space-time itself. You've arrived in the era of dark energy, the invisible hand that's pulling on the universe like it's made of taffy. You can't see it, you can't touch it, but it's bending reality in a way that should be impossible. It's making the universe accelerate. Let that settle in for a second. The expansion of the universe isn't slowing down under gravity's pull, it's speeding up. Galaxies are flying apart faster and faster over time, like glitter hurled from a spinning fan. And the only explanation scientists can offer right now is something we've labelled, helpfully and totally not confusingly, dark energy, which tells you absolutely nothing. It's like naming a weird smell mystery gas and calling it a day. But mystery or not, it's here. It makes up roughly 68% of the total energy content of the universe, and it's not pulling objects through space, it's expanding space itself. The vacuum is getting roomier. The grid of space-time is stretching at every point, not just between galaxies, but within the very fabric of the cosmos. And that has implications for curvature. See, when Einstein first tackled gravity, he thought the universe had to be static, a steady stage. So he introduced something called the cosmological constant, a fudge factor that would balance gravity and keep the universe from collapsing. Then Edwin Hubble came along and showed that galaxies are flying apart. Expansion was real. Einstein called the constant his greatest blunder. But now, it turns out the cosmological constant, or something like it, might be real after all. The universe is expanding again, and the cosmological constant has returned as a candidate for dark energy. Historians still argue whether dark energy is truly constant or something more dynamic, a quintessence field, for example. That name sounds like a perfume line, but in cosmology, it refers to a hypothetical energy field that varies over time. If it's real, it might explain why expansion is accelerating now, but wasn't always this pushy. And the curvature, it's responding. Imagine blowing up a balloon. At first, the rubber is tight, pushing back, but keep inflating and the surface stretches thinner. The same goes for space-time. As it expands, its large-scale curvature flattens. But here's the twist. If expansion keeps accelerating, space-time could stretch so much that it breaks all previous rules. Enter the speculative endgame, the Big Rip. In this scenario, dark energy doesn't just cause expansion, it accelerates it to a catastrophic degree. Galaxies separate, then star systems, then planets, then atoms. Eventually, even space-time itself rips apart. Curvature doesn't go infinite, it goes negative, accelerating to such a degree that no structure can survive. Gravity loses, bonding forces give up. You do not want to be around for this. Will it happen? Well, it depends on the nature of dark energy. If its strength remains constant, the universe expands forever, coasting into a cold, empty heat death. If it weakens, gravity might claw back a bit. But if it strengthens, the Big Rip is on the table, and the limit of space-time bending wouldn't be a dense, compact singularity. It would be the moment space-time stretches itself to pieces. You fly between distant galaxies now, farther than light from one could ever travel to the other in the time since the Big Bang. That's the real kicker of dark energy. It's creating cosmic horizons, invisible boundaries beyond which we'll never receive information again. Not because the light can't catch up, but because space between us and that light is expanding faster than the light can travel. It's a lonely future. Each galaxy group becomes its own island. Communication cuts off. The observable universe shrinks from within, even as the real universe grows. You start to understand why astronomers keep saying observable universe like it's a necessary disclaimer. There's always more beyond what we can ever hope to see. And if you're wondering, yes, this has a real effect. Cosmologists use curvature to test models of dark energy. The angles of distant galaxies, the apparent sizes of ancient sound wave patterns in the early universe. We call them baryon acoustic oscillations, which is just a fancy name for ancient cosmic ripples. They all reveal how space has curved over time. Quirky fact, if you draw a triangle in flat space, the angles add up to 180 degrees. In positively curved space, like a sphere, they add to more than 180. In negatively curved space, like a saddle, it's less. Cosmologists have done this, well, the cosmic version, using light from distant quasars and galaxies, and the result? The universe appears flat, but just barely, a whisper away from curve. Which brings us back to the big question, is there a limit to how much space-time can bend? Dark energy suggests that curvature isn't just a local phenomenon, it's cosmic and accelerating. There may not be a maximum in the traditional sense, but there is a trajectory, a fate, a stretching so intense that space-time itself either thins into perfect flatness or rips apart like an old pair of sweatpants. You drift now through this thinning cosmos. The gaps between galaxies grow. The light of ancient stars fades. The whispers of the early universe become echoes, then silence. But the bend is still there. Not a steep dive like in a black hole, but a long, slow pull. A universal arching that turns space into time and distance into destiny. And you realise curvature isn't always a sharp spike. Sometimes it's a slope, a slow, inevitable tilt towards something final. You're gliding down that tilt now, and space-time is still bending. You're still gliding, still weightless, still drifting through the thinning fabric of a universe pulled tight by dark energy's quiet, insistent fingers. But now, something itches at the back of your mind. A question that's been there all along, hidden behind all the fireballs and frozen starlight and noodle-themed near-death experiences. What if this bending doesn't just stretch? What if it snaps? Can space-time tear? It's a troubling thought. One that makes even seasoned physicists rub their temples and mutter things like, well, define tear. Because space-time, for all its cosmic resilience, isn't immune to the theoretical idea of breaking. Under certain conditions we're not entirely sure can happen, but which the math doesn't rule out, the curvature of space-time might not just bend, it might rupture. You float closer to the edge of that possibility, a place where the curves aren't smooth or sweeping, but jagged, violent. The geometry here isn't elegant anymore, it's angry. One of the wildest ideas, topological defects. These are like cosmic birthmarks, irregularities in the structure of space-time itself, left over from the early universe. Imagine you're knitting a scarf and you drop a stitch. Now imagine that scarf is the universe. That's what a defect might be. There are different types, domain walls, monopoles, and cosmic strings. And yes, cosmic strings are just as ridiculous and wonderful as they sound. These aren't strings like the ones you wrap around a gift. They're one-dimensional objects predicted by some grand unified theories. Incredibly thin, yet fantastically dense. One string could stretch across the universe and still weigh more than the entire Earth. If they exist, they'd curve space-time around them in a strange conical way, like a wedge of space had been removed and glued back together badly. You circle around one now, or at least you imagine it, because we've never actually observed a cosmic string. Historians still argue whether we ever will. Some say they were a passing phase in the universe's youth, gone before the first stars even blinked on. Others say we're still swimming through them, just too clumsy to notice. But if cosmic strings do exist, and two were to collide, or a loop were to collapse, it could release titanic amounts of energy. Enough to bend space-time abruptly, maybe even snap it. Which brings us to singularities again. Black holes are the celebrity examples, but they're not the only place the math misbehaves. Under certain exotic conditions, you can get naked singularities, singularities without an event horizon, fully exposed. Nothing preventing the rest of the universe from seeing them. It's like space has a hole in it with no warning label. Einstein's equations allow for them, but most physicists are deeply uncomfortable with the idea. Hence the cosmic censorship conjecture, a sort of theoretical fig leaf suggesting that the universe always hides its singularities behind event horizons. It's not proven, of course, just hoped for. Because a naked singularity wouldn't just bend space-time, it would break causality. Events could happen before their causes. Light paths could loop. Information could arrive before it was sent. That's not just weird. That's threatening to the very idea of physics. You look around this stretch of speculative space and begin to notice something else. Small bubbles forming in the vacuum. Not soap bubble light, but mathematical instability. This is the territory of false vacuum decay. Another theoretical way space-time might tear. Here's the short version. The vacuum of space, the lowest possible energy state of the universe, might not be the true lowest state. It might just be a false vacuum, metastable and pretending to be the bottom. If it's not the true vacuum, then a quantum fluctuation could one day cause a tiny bubble of actual vacuum to appear. That bubble would expand at the speed of light, devouring everything in its path and rewriting the laws of physics inside it. Sleep well. This isn't science fiction. It's based on real, if highly speculative, quantum field theory. Physicists have done the math, and while no one's particularly worried, it would happen without warning, so it's not worth stressing about. It still suggests something profound. Space-time isn't invincible. It might fail, it might tear. Even in more mundane terms, you can imagine space-time folding in on itself through closed time-like curves, loops in time caused by certain solutions to Einstein's field equations. These allow for time travel of a kind, at least mathematically. They require massive rotation, like in a Kerr black hole, or exotic matter with negative energy density. They bend space-time so severely that time itself circles back around. And yet, they might not tear anything. The fabric could hold, just in a knot that violates everything you thought you knew about linear causality. Is there a structural limit? A pressure point where the stretch becomes too much? That's the open question. If space-time has a tensile strength, we don't know what it is. The Planck scale, a realm where quantum and gravitational effects become equally important, might represent the boundary. The Planck curvature so sharp that no classical space-time can exist beyond it might be the upper limit. But what happens at that edge? Does space-time fracture into fragments? Does it fizzle into quantum foam? Or does it give birth to something new? You drift away from the stringy scars and the bubbling vacuums back into smoother space. But you carry with you the uneasy feeling that not all bends are graceful. Some are accidents, misprints, tears in the tapestry. And while we haven't seen space-time rip yet, haven't witnessed it snap, splinter or burst, we haven't ruled it out either. It might not take a black hole, it might take a glitch, a moment where reality forgets how to hold itself together. And when that happens, what comes next? You've floated through singularities and sizzled through the early universe. You've watched space stretch and felt time lag like a tired phone app. So maybe you're starting to think, okay, space-time bends, but what if it could fold? Not just curve around something, but really fold, in on itself, over itself like cosmic origami. Because if bending can stretch distances and stall clocks, what happens when space-time cheats the distance altogether? Welcome to the strange, seductive concept of wormholes. You're drifting toward one now, not in the sense that you can see it, you can't, but in the sense that the math is hovering in your brain like an unskippable ad. A wormhole is a hypothetical tunnel through space-time, a shortcut connecting two distant regions via a path outside of normal geometry. It's as if the universe were a folded sheet of paper and someone punched a pencil through 2 points to create a hidden bridge. Left side of the galaxy, right side of the galaxy, doesn't matter, just step through. In theory, wormholes aren't just a sci-fi trope, they're legitimate solutions to Einstein's field equations. One of the first known was discovered in 1935 by Einstein and physicist Nathan Rosen, called the Einstein-Rosen Bridge. Sounds majestic, but it's not particularly friendly. That model links two black holes, but only for an instant, and only if you don't mind being obliterated by tidal forces before you even halfway arrive. Still, the seed was planted. Later solutions imagine more stable versions, tunnels you could actually travel through. If you could keep the tunnel open, and if it didn't collapse the moment you stepped inside, and if it didn't require more energy than exists in the observable universe, then sure, it's totally practical. There's just one tiny problem. You'd need exotic matter to hold it open. Not exotic as in weird cheese, but exotic as in negative energy density. Stuff that pushes outward instead of pulling in. Basically the opposite of what gravity does. It's not impossible, strictly speaking. Certain quantum phenomena, like the Casimir effect, produce tiny regions of negative energy between closely spaced plates. But turning that into a structural beam to support a transgalactic bridge, still a stretch. Literally. The moment you start to imagine climbing into one of these things, you realise the curvature required isn't just dramatic, It's unfair. The space-time at either mouth must bend inward, forming a throat that connects two regions like a straw through the fabric of reality. If normal space is a valley, this is a funnel, tightly curved, narrowly focused, and full of mathematical headaches. But what's truly bonkers? Wormholes could allow time travel. Suppose you move one end of the wormhole at near light speed, then bring it back. Time dilation means the travelling mouth would have experienced less time than the stationary one. So if you step into the younger mouth, you could emerge from the older one, effectively stepping backward in time. Congratulations, you've just created a closed time-like curve. Historians still argue whether this violates causality, or if the universe would self-correct to prevent paradoxes. Some physicists think nature has a mechanism, still unknown, that forbids time loops. Others suspect the math doesn't lie. If wormholes are possible, time travel might be baked in. Quirky idea. There are entire speculative frameworks where wormholes aren't built, they just exist. Tiny ones, left over from the early universe, flickering in and out of space-time like background static. Some suggest these quantum wormholes might connect distant particles, or even form the threads of entanglement itself. You drift beside a theoretical wormhole now, its mouth glowing softly in your imagination, like a portal drawn in pencil on the back of a napkin. It warps the space around it so completely that distances become irrelevant. 2 billion light-years away, one step. But as you get closer, the tunnel flickers, collapses, reforms. It's not stable, not yet. The geometry fights against itself, trying to snap shut like a rubber band. And you start to feel it again. Curvature as rebellion. The universe doesn't like being bent too sharply. It tolerates black holes. It endures inflation. But wormholes? These require a level of control that reality doesn't seem eager to hand over. Still, you wonder, what if some advanced civilization has figured it out? What if they've harnessed exotic matter, stabilized the throat, and stitched together a cosmic subway system? A handful of theorists suggest that if wormholes exist, they might be camouflaged as black holes. You see one end, a gravitational monster, but not the escape hatch on the other side. Could those jets of radiation we see blasting out from quasars be the afterglow of matter exiting a wormhole elsewhere? Probably not. But probably not isn't quite the same as definitely not. And then there's the more fringe view, that our entire universe is inside a wormhole, that what we see as cosmic expansion is just the inside of a curved passage stretching open from another, higher dimensional space. The math for this idea shows up in certain versions of string theory and brain cosmology, where our universe is a four-dimensional bubble floating in a higher dimensional bulk. You rub your eyes, it's too much. The bends are everywhere, around stars, in the void, through black holes and maybe through tunnels no one's walked. And yet, the universe seems to handle it. The fabric doesn't rip, at least not obviously. It stretches, warps, flows like lava beneath the feet of your understanding. So can space-time fold into a wormhole? Yes, on paper, with conditions, with wild assumptions, with math that strains the edge of belief. But can space-time allow it in reality? That's the part we still don't know, and maybe that's the limit. Not in curvature itself, but in the permission. The universe allows many things, but it doesn't give out free passes. Wormholes might exist, but if they do, they're rare, fragile, hiding. And they bend space-time so tightly, so deliberately, that even thinking about them makes your head tilt sideways. You float on. The wormhole behind you winks out like a dream you almost remembered. The shortcut didn't take, so you keep drifting forward. The long way. The wormhole fades into the distance like a vanishing thought, and you find yourself in a very different kind of place. Not grand or luminous, but tiny. Unreasonably tiny. Shrunk down far below the width of a proton, past atoms, past quarks, until you're knocking politely at the front door of the Planck scale. You knock, the door kicks you in the face. This is not a friendly place. It's not empty space as you know it. It's quantum foam, a name that sounds like a sci-fi milkshake but hides the fact that you're about to have your sense of scale shattered. At the Planck length, about 1.616 times 10 to the negative 35th meters, space-time stops being smooth. You know how fabric looks solid until you get really close and see the weave? Same deal here. Space-time becomes grainy, frothy, uneven. You're floating in a region where geometry itself has become, well, suspicious. You thought you understood curved space-time back when it bent around planets or black holes. That was beginner-level stuff. Here, the very concept of bend breaks down. There is no continuous surface anymore. Instead, the geometry fluctuates. Space warps one way, then the other. Time twitches. Directions lose meaning. You're in a place where space-time vibrates, not like a harp string, but like a nervous breakdown. What's curving space-time here? Nothing obvious. There are no planets or galaxies, no energy fields or mass to pin blame on. The curvature is intrinsic, baked into the very quantum structure of the vacuum. It pops and fizzes with virtual particles, brief, ghostly forms that exist and unexist in blink-length bursts. And with every fluctuation comes a tiny curvature, not in a sweeping arc, but in wild, jittering spikes. Imagine trying to draw a straight line on a trampoline being punched from below by invisible fists. That's quantum foam. That's the baseline of reality. It's enough to make you nostalgic for black holes. Mainstream physics still doesn't have a single unified theory that describes this place. General relativity handles the big stuff beautifully, but it stumbles here, hard. Gravity, in Einstein's version, requires smooth geometry. But quantum mechanics, it demands randomness, uncertainty, probabilities, not certainties. So far, no one's managed to get these two theories to sit at the same lunch table without flipping the tray, but we have contenders. One of the leading ones, loop quantum gravity. It's not as flashy as string theory, no 10 dimensions or vibrating strings, but it proposes something deeply elegant, that space itself is made of discrete units, tiny loops, interwoven like a chainmail made of geometry. You don't move through space, you move from loop to loop. You don't bend space, you reshuffle its loops. And in this model, curvature is not continuous, it's granular, a series of quantum steps, like a staircase disguised as a slide. No matter how tightly you bend it, there's a built-in limit. The loops don't break, they just reconfigure. Historians still argue whether loop quantum gravity has the mathematical strength to handle full-on black holes or inflationary universes, but it does offer something valuable, a maximum curvature, a ceiling beyond which space-time says, nope, I don't bend that far. This matters because it might save us from singularities. In loop quantum gravity, a black hole doesn't end in a point of infinite density, it ends in a bounce. The loops reach peak density and then recoil, possibly spawning a new region of space-time. Think cosmic CPR. Now, let's shift goggles for a moment and peek into string theory. Instead of loops, string theory imagines that everything, from electrons to gravitational fields, is made of tiny vibrating strings. Each vibration represents a different particle, like plucking a string on a cosmic guitar. But these strings don't live in 4D. They require 10 or 11 dimensions, depending on the model. Most of those dimensions are curled up so tightly you'd never notice them, like spare shoelaces tucked into your socks. In these extra dimensions, curvature takes on exotic forms. You can have Calabi-Yau manifolds, complex shapes folded in ways that let strings vibrate just so. The curvature in string theory isn't just around mass, it's baked into the extra dimensions, and if those folds twist the right way, they can determine the physical laws of the universe you end up with. Gravity, particle mass, even the speed of light. Quirky detail? Some versions of string theory suggest that gravity is weak, not because it's inherently lazy, but because it leaks into extra dimensions. That might be why we can balance a spoon on one finger but not on a laser beam. Back in the quantum foam, none of these models is fully proven. But they all agree on one thing: space-time has structure. It's not an empty backdrop, it's a thing. And that thing might come in finite pieces, which leads to a tantalizing idea. Maybe space-time doesn't allow infinite curvature. Maybe the closer you get to that singularity, the more quantum effects push back. The loops lock, the strings resist, the foam clots. Space-time hardens before it can break. Could this be the real limit? Not the event horizon of a black hole, not the cold stretch of dark energy, but right here, at the smallest scale, the place where curvature stops being smooth and starts being chunked, where the fabric is no longer fabric but stitched patches of quantum law. You drift onward, even smaller now, passing through regions where even time flickers. A Planck second, 10 to the minus 43 seconds, is the smallest meaningful unit we know. Any faster, and causality may not apply. Curvature here isn't just sharp, it's uncertain. And this uncertainty may be the answer. Maybe space-time can bend and bend and bend right up to the quantum limit, and then it doesn't snap, it fuzzes. You drift through the blur of fuzzed-out geometry, still shrinking, or at least conceptually shrinking, into realms where measurement itself becomes suspicious. You're now deeper than the Planck scale, if such a thing can even be said without the laws of physics giving you a side-eye. Space-time here doesn't resemble fabric anymore, it doesn't resemble anything, and yet the math persists. Somewhere in the soup of loops and strings and whispering quantum fields, you find yourself caught in two competing dreams: loop quantum gravity and string theory. Two visions of what might lie beneath the smooth veil of Einstein's cosmos. You land gently on a loop, not a physical loop. Nothing here is physical anymore, but a structure, a pulse in the undercurrent. In loop quantum gravity, these loops are the smallest indivisible units of space, tiny patches of area that, when woven together, form the illusion of continuous reality. No more smooth curvature, instead, a stepwise geometry. Think pixel art, not HD film. The loops connect in networks called spin networks, which evolve into spin foams, structures that describe the geometry of space-time itself in motion. You're not floating through space, you're moving across this quantum scaffolding, like a spider delicately tiptoeing across threads of pure mathematical tension. And here's the wild part. In this theory, volume and area are quantized. You can't have any value you like, just specific amounts. It's like a Lego set. There's no half brick, which means curvature also comes in quanta. It can only bend so far before it hits the next allowable unit of angular change. Is that the limit? Maybe. In loop quantum gravity, the maximum curvature appears just before you reach what classical physics would call a singularity. But instead of infinity, you bounce. The quantum loops fight back. They compress, sure, but then they recoil. This recoil is what some theorists think could create a new expansion, a new universe. The technical term, a quantum bounce. But let's be honest, it's the universe doing a somersault because it refuses to fold in on itself. And now you drift sideways in theoretical space, into the other contender, string theory. Here, the universe isn't made of point particles or discrete loops. It's made of tiny vibrating strings, each one about the Planck length long, stretched taut through 10 or 11 dimensions. The flavour of the vibration determines what kind of particle the string plays, like a violin string making different notes. Gravity? That's just one of the notes. But these strings don't vibrate in empty space. They vibrate in folded dimensions called Calabi-Yau manifolds. Beautiful, compact geometries so complex they could make a kaleidoscope blush. You don't see these extra dimensions because they're curled up, tighter than anything our instruments can detect. And curvature in string theory? Oh, it's everywhere. Space curves within the extra dimensions, time twists, fields wrap around higher dimensional surfaces called branes. Whole universes might be stacked like pages in a multi-dimensional book, each page a brane, each brain bending slightly based on the mass and energy it contains. Fringe idea. We might live on one of those brains trapped in 3 spatial dimensions, while gravity leaks into the extra ones. This would explain why gravity seems so weak compared to the other forces. It's not weak, it's just spread out. And you, dream gliding through all of this, begin to sense that curvature isn't just a property of space-time, it's the language the universe uses to write itself. Whether in loops or strings, the bends encode information, how particles move, how forces interact, how time unfolds. Quirky detail. In string theory, black holes don't end in singularities. Instead, they are fuzzballs, smeared out configurations of strings that prevent true collapse. It's another way of saying that infinite curvature might never happen, because quantum structure smears the sharp point into a fuzzy blob of possibility, which honestly feels like a pretty cosmic loophole. No singularities, just aggressively compressed string spaghetti. Historians still argue whether either theory is right. Neither has produced direct testable predictions at human accessible energies, but both offer tantalizing hints that there is a maximum, a cap, a point at which curvature cannot go further, not because it runs into a wall, but because reality is too grainy to bend any tighter. You float now between 2 visions. In one, space is a web of loops. In the other, it's a vibrating chorus of strings. Both claim to tame the singularity. Both claim to put a ceiling on the bend. And perhaps the truth lies in some strange hybrid, a theory not yet born, a union of loops and strings, grains and chords that finally stitches quantum mechanics and gravity into one seamless and slightly bend-resistant whole. For now, though, the loops and strings continue their eternal dance. You pass through a spin foam and feel the discrete tick of geometry reforming beneath you. You brush the surface of a Calabi-Yau shape and feel a kind of folded time, curved not in directions you understand, but in whispers your bones remember from before bones existed. Everywhere you look, the message is the same. Curvature has a rhythm. It may stretch and flex and loop, but it does not break. It quantizes. You feel your motion slow now, not from friction, there is none, but from something more fundamental. A kind of cosmic hush falls over everything. The dance of loops dims, the strings go quiet. You've passed through the densest geometry, the loudest notes of curvature, and now you feel the silence of structure itself. Time to rest. The lights are dimmer here. The sharp bends have softened. The loops unwind. The strings fall still. You're not falling anymore. Not forward, not inward, not toward anything. The fabric of space-time no longer resists or flexes or whirls. It simply exists. And for the first time in a long, long while that feels like enough. In this quiet place, curvature no longer howls. It hums, low even, continuous. Like the gentle pull of the earth under your feet when you're lying in bed, listening to the fan spin. Like the sound your heart makes when it's not chasing anything. Just being. The quantum foam settles, its ripples calming into subtle vibrations beneath thought itself. The brains curl gently, not from tension, but from memory. The structure of reality no longer writhes under pressure, it exhales. And you? You're still here. Not a singularity, not a spaghettified strand of regret, just a mind floating in the softened geometry of a universe that has finally remembered how to rest. So let it rest. Let the loops drift out of focus. Let the strings blur into background rhythm. Let the last sharp angles round themselves into dreams. You've made it through the bend. Sleep now. You stir gently in the softened folds of space-time, still cocooned in the lingering quiet of loops and strings. But the hush doesn't last. A new thought nudges at you, like a tap on the shoulder from a teacher who knows you're dozing in class. What happens when gravity gets too strong for the math to handle? It's a real question, not rhetorical. Because we're not talking about strong in the everyday sense, like lifting weights or resisting a sneeze. We're talking about gravitational intensity so extreme that the equations meant to describe it start coughing up gibberish. You've seen some of this already, inside black holes, at the start of the universe, and maybe in the flirtations of wormholes and false vacuum decay. But now, we're zeroing in on the numbers themselves, the limits of the math, and how far we can push the machinery before it seizes up. Let's rewind a bit. Einstein's general relativity works like a dream under most conditions. It gives us elegant, sweeping curvature, beautiful predictions, and even a little time dilation magic to keep GPS satellites honest. But it's still a classical theory. It treats space-time as a smooth, continuous surface, and it hates infinities. You introduce infinite density, the math shrugs. You push curvature toward infinity, the equations curl up like burnt paper. They don't say, here's what happens, they say go ask quantum physics. And quantum physics, it's not thrilled about gravity. The problem is that gravity, unlike the other three forces, isn't described by a particle-based quantum field theory. There's no confirmed graviton, no massless spin-2 particle whose field you can plug into the quantum machinery. All the other forces, electromagnetism, the strong force, the weak force, they have particle mediators. They play nice with quantum theory. But gravity, it refuses to join the party. Every attempt to make a quantum field theory of gravity runs into infinities that can't be renormalized. The math starts screaming, divide by zero, and everyone backs away slowly. This is why physicists spend entire careers chasing a theory of quantum gravity, a single framework that would unify the geometric power of relativity with the probabilistic madness of quantum mechanics. We've got candidates. You've met two: loop quantum gravity and string theory. There are others: asymptotic safety, causal dynamical triangulations, emergent gravity, but none have yet given us the full key. And until we get that key, there are places in the universe we can't model, mathematical blind spots, zones where our best tools break. Take the Planck curvature, the theoretical maximum curvature space-time could endure before quantum effects take over. It's not just a number, it's a limit built into the very constants of the universe. If curvature is a measure of how space-time bends, then at the Planck scale, you're talking about bending so sharp it would make a corkscrew jealous. Push gravity past this point, and space-time becomes meaningless in the way a mirage becomes meaningless once you're standing inside it. There's no further, no sharper, no more bend, just a shift into something else. And this brings us to a chilling thought. What if gravity doesn't just break the math? It breaks the universe. This idea shows up in scenarios where gravity gets strong enough to overwhelm all other forces. Imagine compressing matter until not even quantum pressure can push back. You get a black hole. Keep going, past that, and you arrive at a singularity. But if the quantum foam pushes back first, you might instead get a new phase of space-time. Fringe thinkers speculate about gravity-induced phase transitions, where space-time itself could change state, like water freezing or boiling, under intense gravitational conditions. Maybe the structure of the vacuum shifts, maybe the dimensionality changes, maybe what we call space stops being a useful idea at all. Here's a mainstream twist. We've started discovering gravitational interactions so powerful, we need computers just to describe them. Gravitational wave astronomy, thanks to LIGO and Virgo, has revealed black hole collisions so extreme that for a brief moment, more energy is released than the rest of the visible universe combined. All of it in gravitational waves. That's not just strong gravity, that's space-time hitting itself like cymbals. The curvature involved in those moments just before merger is off the charts, and while general relativity describes them well enough, for now, we're probably seeing the edge of where the math stays friendly. If the masses were higher, or the distances smaller, or the spins more chaotic, we might finally cross into a zone where quantum gravity steps forward and says, "I'll take it from here." Historians still argue whether we've already seen hints of this. Some gravitational wave events have small anomalies, tiny deviations from what general relativity predicts? Are they noise, calibration errors, or whispers of physics beyond Einstein? We don't know, yet. And while we're talking about the limits of math, let's not forget the cosmic censorship conjecture again. It's a promise, more than a theorem, that singularities will always stay hidden behind event horizons, but if gravity gets too strong, if the curvature spikes in just the wrong way, that promise could break. Naked singularities would expose the raw failure of math, right there in observable space, not hidden, not abstract, a place where predictions end, where you feed in inputs and get nothing, or worse, everything. It's the physics equivalent of a blue screen. You feel that tension now. That sense that curvature isn't infinite but bounded. Not by walls, but by structural limits, by the failure of models to accommodate scenarios where energy densities go rogue. So is there a cap? Maybe it's not a wall of fire. Maybe it's not a singularity or a bounce or a tear. Maybe it's just a line in the math, a horizon in our equations past which lies the next theory. The theory we don't have yet. The theory that will finally tame gravity. The one that doesn't flinch at infinite bends. The one that rewrites too strong into something we can finally understand. Until then, we push the math. We listen to the gravitational waves. We tweak our models. We build bigger detectors. And we hope that somewhere in the background noise, space-time is whispering the answer. You're drifting again. Forward, inward, downward. Though none of those directions really exist out here. Space is too bent to care about your old compass points, and time, well, time has become more of a suggestion. Ahead you feel it, a horizon. Not the kind you see at sea, not the edge of the Earth, not even the event horizon of a black hole. This one is more abstract but far more final, the Planck wall. You've been approaching it for a while without knowing. It's the limit beyond which even your best theories stop playing fair. You reach out a hand, not literally, but in that deep brain metaphorical sense, and you can almost touch it. It hums, it bristles. It's not a barrier made of energy or matter or force, it's a boundary of definition. Because beyond this, space-time isn't just curved, it's uncertain. The Planck length, about 1.616 times 10 to the negative 35th meters, isn't just small. It's the smallest unit of distance that makes any physical sense. Try to measure anything smaller, and the very idea of position dissolves. The Planck time, about 5.39 times 10 to the negative 44th seconds, isn't just quick. It's the tick of a clock that no longer ticks, because below it, time as we understand it is more jazz improv than metronome. This is where your measuring stick turns to soup. The smooth fabric of space-time, so useful, so elegant, becomes grainy, bumpy, incoherent. You're standing on a cliff made of physics, and on the other side, nobody knows. One idea physicists toy with: space-time might be quantized at this scale. We've mentioned this: loops, strings, spin networks. But here's where it gets real. No more pretending that space is a continuous stretch of rubber. No more smooth curves. At the Planck scale, space-time may come in chunks, discrete little units, digital instead of analog. If true, that means you can't just keep increasing curvature forever. Imagine trying to fold paper tighter and tighter until you're crumpling it between atoms. Eventually, the structure of the paper gives out. That's space-time at the Planck wall. It can't bend further because it has structure. There's a grid beneath the grid, a cosmic Lego set. This brings us to the idea of a minimal length scale, a physical limit to how small anything can be. Not because of technological constraints or engineering limits, but because nature itself says, that's it, that's as far in as you go. Historians still argue whether this minimal length is fundamental or just a byproduct of our incomplete theories. Is it a true wall or a fog bank? Some argue that even if you could probe smaller scales, quantum uncertainty would blur everything beyond usefulness. Others think we may eventually discover sub-Planckian structure, a deeper layer of reality. superstrings, quantum graphs, foamier foam. But most agree, something changes here, and here's where it gets unsettling. You know how black holes represent a kind of maximum curvature? A point where gravity folds space and time into a knot? Well, if the Planck wall is real, then black holes never actually reach that infinite point. The curvature approaches the Planck limit, and then something else takes over. What happens next? That depends on who you ask. Loop quantum gravity suggests a bounce. The black hole's core never hits a singularity. Instead, space rebounds. The collapse inverts. A white hole might even form, a time-reversed black hole that expels matter instead of sucking it in. Wild stuff. String theory, on the other hand, replaces point particles with extended objects, strings, brains, that can't collapse to zero volume. This smears out the singularity and replaces it with a fuzzball or a stringy tangle. Curvature still hits extreme values, but it's regulated by the geometry of strings themselves. And then there are models like asymptotic safety, which propose that the strength of gravity stops increasing at small scales, like a roller coaster that levels out instead of launching you into the sun. The equations stabilize, the curvature maxes out, not because it breaks, but because it finds balance, a fixed point in the wild sea of quantum gravity. You drift toward it, feeling the mathematics swirl. The constants of nature begin to whisper, Planck's constant, the speed of light, Newton's gravitational constant, all woven into a boundary you can't cross, not physically, not conceptually. Here, space-time might become non-commutative, a fancy way of saying that coordinates stop behaving. In our everyday world, if you move left then forward, it's the same as moving forward then left. But down here, that breaks. Order matters. Position becomes a thing you can only define in fuzzy probabilistic ways. And time? Time might not exist here, not as a dimension, not as a river, not even as a ticking sequence. Some quantum gravity models replace time with causal relationships, not when something happened, but how events influence each other. The before and after become tools, not truths. And you're not falling anymore. You're vibrating, not in space, but as space. Whatever's left of your conceptual body is now part of the geometry. You're not separate from the fabric. You're a note in the quantum drum skin. You realize something profound. Maybe space-time doesn't bend forever. Maybe it quantizes, condenses, folds into data. And just as matter can't be crushed past a certain point without changing phase, from gas to liquid to solid, maybe space-time has phases too. States of geometry, modes of being. The Planck wall might not be a wall at all, it might be a transition, from space-time as structure to space-time as information. A change in what it means for reality to have where and when. You settle at the boundary, the hum of maximum curvature vibrating like a cosmic dial tone. Nothing more to see, no deeper to go, just the edge of bending, just the beginning of understanding. You rest at the edge of the Planck wall, where time trembles and space refuses to behave. It's not peaceful, exactly, but it's not hostile either. It's something worse, indifferent. Here, the universe doesn't care about your instinct to ask how much or how far or how fast. Those were good questions, useful questions, but you've outgrown them. And now a new one whispers its way into your mind. What does it cost to bend space-time? You've felt the bends. You've seen space dip around planets, twist near stars, collapse inside black holes. But you haven't asked the deeper question, the energy cost. Because yes, curvature isn't free. Just like bending steel or stretching rubber takes effort, warping space-time requires energy. And in this universe, energy always keeps a receipt. In Einstein's language, mass and energy are what curve space-time. That's the whole point of the Einstein field equations. G mu nu equals 8 pg over c to the fourth power t mu nu. On the left, geometry, curvature. On the right, stress energy, matter and energy content. Two sides of the same cosmic ledger. This means that every curve you feel in space is backed by energy somewhere. The tighter the curve, the more energy is crammed into the region causing it. Want to warp space enough to hold a moon in orbit? You need a planet. Want to warp it enough to hold light hostage? You need a black hole. Want to create a shortcut across the galaxy? You'll need more energy than your species has used in its entire history. You begin to see curvature as a currency, a way the universe spends energy to shape geometry. And like any economy, there are limits. Try to bend space-time too much without the corresponding mass energy, and you'll fail. Try to stuff too much mass energy into one point, and you get a singularity. It's not a loophole, it's a red line, one enforced not by law, but by the nature of the equations themselves. Let's get practical. Suppose you want to build a gravitational lens, a mass so dense it bends light dramatically, like a telescope made of space itself. Astronomers already use galaxy clusters to do this. These massive structures act as natural lenses, bending light from galaxies far behind them. Now imagine trying to build one deliberately. You'd need mass, lots of it. Maybe arrange planets, then stars, then black holes. The energy cost scales up fast. More curvature, more energy. And it's not just mass. Pressure, momentum, and even tension contribute to the stress-energy tensor. That's right. Tension can curve space. You're not imagining things when you feel stress weighing on you. In general relativity, even stretched rubber bands and high-pressure gases influence geometry. Want an even weirder twist? Vacuum energy, the energy of empty space, can also curve space-time. That's what dark energy is. Not particles, not waves. Just the energy of nothing stretching the cosmos like warm dough. It's expensive, in a different way. Quirky fact for your sleepy trivia bank. In 2004, physicists calculated the energy needed to maintain a stable traversable wormhole. The result? You'd need negative energy equal to the mass of Jupiter to keep a wormhole just a few meters wide, and that's assuming you can even find or generate negative energy in bulk, which is, not something we've mastered in the lab. So curvature isn't just about geometry, it's about resources. The deeper the dent, the greater the price. This concept also shows up in gravitational waves. When black holes collide, they emit ripples in space-time that stretch and squeeze the cosmos. These aren't metaphors. Detectors like LIGO have measured these ripples. And what are they made of? Energy. The energy of motion and mass converted into pure space-time vibrations. In one spectacular event, GW150914 if you want to impress someone at a dinner party, two black holes collided and released about 3 solar masses worth of energy in gravitational waves in a fraction of a second. That's energy spent to make space dance, which leads you to another insight. Curvature can radiate. When things bend space violently enough, they can lose energy by creating more curvature. It's like a guitarist strumming so hard the strings shake the stage. Space-time isn't passive, it echoes. And this exchange between geometry and energy works both ways. A collapsing star curves space. That curvature funnels more mass inward. More mass means tighter curvature. It's a feedback loop, one that ends with either a black hole or a spectacular explosion. You begin to understand why physicists treat the Einstein equations like a balancing act. They're not about causes and effects, they're about equilibrium. Curvature must match energy. Energy must explain curvature. If they don't balance, the math says no. So when you ask, is there a limit to how much space-time can bend? What you're really asking is, can you afford it? Because the limit might not be geometric, it might be economic. There may be configurations of space that are so tightly curved, so extravagantly folded, that they could exist mathematically. But the energy cost to build or maintain them would exceed the resources of any region of the universe. Not forbidden, just impractical. Theoretical castles in an energetic sky. And yet, nature does spend big when needed. The early universe was wildly curved. Black holes still bend space to the point where light can't escape. Inflation, gravitational lensing, neutron stars, galactic mergers. These are expensive operations. But the universe budgets wisely. It never bends without funding. It never curves without consequence. So maybe there's no cosmic law that says, you cannot bend space-time beyond this number. Maybe it just comes down to, you can't afford it. You float now in a region of space barely touched by mass. The curvature is so mild it's almost flat. And yet, you feel the cost of every nearby presence. That star over there, a billion-year mortgage and gravitational debt. That black hole, a payoff in entropy and time, and you're just passing through, a temporary distortion, a wrinkle with a brief budget. The math holds, the tab is always paid. Even in dreams, you drift now like a tired surveyor charting the wide-scale geometry of the universe itself, one cosmic continent at a time. No black holes here, no quantum foam nipping at your ankles. Just the big picture, the shape of it all. And spoiler, it's complicated. You've heard people say the universe is flat, that it has no edge, that it's infinite, or maybe finite, expanding, looping, curling, stretching. Some say it's like a balloon, others say it's a hypersphere, and everyone has a diagram with way too many arrows. So let's get serious. You're here now, floating somewhere between galaxies, far from local curves and gravitational drama. Time to ask, what is the shape of the universe? And deeper still, can the universe itself be curved? Short answer, yes. Long answer, yes, but in several different ways, depending on who's asking and how much coffee they've had. Let's break it down into the three most common options: open, closed, and flat. You float now with a yardstick in your hand, a cosmic measuring tool. You decide to draw a triangle, you measure the angles. If they add up to exactly 180 degrees, congrats, the universe is flat. If they add up to more than 180, you're in a closed universe, like drawing a triangle on the surface of a sphere. Space curves back on itself. Less than 180? Open universe. Think of a saddle shape. Distances get weird. Parallel lines eventually diverge. Back in the early 2000s, satellites like WMAP and later Planck mapped the cosmic microwave background, the afterglow of the Big Bang. The patterns of temperature fluctuations in that baby photo of the universe were used to determine its geometry. The result? Drum roll, flat. Or more precisely, very close to flat, within a small margin of error. The triangle you drew adds up to something like 179.999999 degrees. That doesn't mean it's perfectly flat, but the curvature is so subtle it could stretch over billions of light years before you'd notice a deviation. Historians still argue whether this means the universe is truly infinite, or just so large and gently curved that we can't detect its boundaries. Flatness doesn't guarantee infinity, it just means we haven't found the bend. But the implications are huge. If the universe is flat, its total energy balance is precariously balanced between expansion and collapse. It means the geometry of space is Euclidean at large scales. Parallel lines stay parallel. Light travels in straight lines, unless bent locally by mass. Geometry behaves itself. If the universe were closed, it would be like living on a 3D version of a sphere. Travel far enough in one direction, and you might return to your starting point. Not because you turned, but because space itself loops. The curvature is positive. Enough mass in the universe could bend it inward like the surface of a globe. In this case, the universe would be finite but unbounded. There'd be no edge, just a constant return. And perhaps one day, that curvature could reverse the expansion, leading to a big crunch, a collapse back into high density, followed by something new. The open model, on the other hand, has negative curvature, like the shape of a potato chip or a horse saddle. Space expands forever, faster and faster, and light from distant regions never returns. This universe would be infinite, cold, and lonely. Its geometry means things get farther apart more quickly than intuition allows. You glide now between models, like a sleepwalker weaving between possibilities. In the flat universe, distances remain honest. Angles add up. Expansion continues gently. In the closed universe, you begin to loop, recognizing constellations that you already passed, warped slightly by curvature. In the open one, you're stretched, pulled along expanding axes that diverge with every heartbeat. Space seems bigger than time knows what to do with. The curvature of the universe as a whole isn't just a question of what shape is it, it's also about fate. Cosmic geometry and destiny are intertwined. Curved inward, collapse, curved outward, eternal expansion, flat, balance, but easily tipped. But of course, the universe isn't that tidy. Even with a flat geometry, dark energy complicates everything. It adds acceleration into the mix, stretching the fabric faster than the mass within can slow it down. So even a flat universe can end in heat death. And here's your quirky footnote for tonight. Some theories suggest that our universe could be multiply connected. That is, space might be flat and looped. Imagine a video game map that wraps at the edges. You could travel infinitely in one direction and still revisit the same regions. This is called a toroidal universe, like a donut. The geometry is flat, but the topology is twisted. In such a universe, you might one day see the back of your own head, if the light loops fast enough and far enough. No evidence for this yet, but it's not ruled out. And now we enter the fringe zone. Simulations, higher dimensional spaces, holographic projections. Some physicists propose that the curvature we observe is just a shadow, an artifact, of a higher dimensional geometry we can't perceive. In these models, our three-dimensional universe is like a membrane, brain, floating in a higher dimensional bulk. In some versions, gravity is the only force that can leak into these extra dimensions. That's why it feels weak. That's why it's hard to unify with quantum mechanics. It's literally escaping the page. You pass through such a model now, you feel the curvature, but you can't see it. It's behind the veil, and yet it shapes everything. The universe may be flat, or it may just appear flat to us. Like looking at a great curve from up close, it feels straight until you back away far enough to see the arc. So is there a limit to how much space-time can bend? You've seen stars bend space. You've seen it loop into holes. You've seen it fuzz out at the Planck edge. But this cosmic curvature might be the ultimate bend. Not local, not violent, just grand. The very shape of everything. The universe still stretches around you wide and quiet like the belly of a sleeping giant. You've traced its shape, watched it bend and swell across billions of light years. And now, finally, a thought sneaks in. What if we didn't have to wait for nature to bend space-time? What if we could do it ourselves? That's right, you're officially asking the sci-fi question. Can we bend space-time on purpose? And not just a little. Not just gravity assists and orbit tweaks. You want the big stuff. You want warp drives. You want shortcuts. You want to fold space-time like laundry and pop out somewhere new, maybe without getting spaghettified or turned into a singularity smoothie. So, can we? Well, the short answer, we don't know how, but the math doesn't say no. Let's talk about the headline act first, the Alcubierre drive. Proposed in 1994 by physicist Miguel Alcubierre, it's a theoretical model that allows for faster-than-light travel without breaking the cosmic speed limit. How? By bending space-time around your spaceship instead of pushing it through space. Here's the idea. You create a warp bubble. Inside, your ship is sitting still, like a lazy cat on a cushion. But the space in front of the bubble contracts, while the space behind it expands. You're surfing a wave of curved space-time. The ship doesn't move, the space moves, and if space-time can move faster than light, which it can, see cosmic inflation, then you just might get to Alpha Centauri in time for lunch. It's elegant, it's beautiful, it's horrifyingly impractical. Why? Energy. Remember how we said earlier that curvature has a cost? This drive needs energy in absurd amounts. Early estimates suggested the negative energy equivalent of a few solar masses. Later revisions got that down to the size of a small planet. then to the mass of a large spacecraft. But it still requires something we don't have: exotic matter with negative energy density. And that's not just a technical problem, it's a physics one. Negative energy is allowed in theory. We've seen it briefly in the Casimir effect, where quantum fluctuations between metal plates create a tiny bit of negative pressure, but we've never found a way to scale that up. Worse, Alcubierre's bubble comes with a nasty surprise. It might trap anything trying to enter it. You can't send messages into it. You can't steer it once it starts. And if it hits something, oof! The tidal forces at the front of the bubble could be catastrophic. You might arrive at your destination with the mass of the bubble ahead of you, concentrated into a fine death ray. Not a great look. Still, the model doesn't violate Einstein's equations, so that little door, it's open, just barely. Now shift your gaze to gravity control, the dream of building machines that can shape space-time the way we build dams and bridges. Could we ever manipulate mass and energy so precisely that we engineer curvature? Well, gravity is weak. Like, unreasonably weak compared to the other fundamental forces. That's why we need whole planets or stars to see noticeable curvature. You'd need something truly massive or exotic. Maybe quantum fields, maybe artificial black holes, maybe dark energy harnessed in a bottle to bend space meaningfully. But here's a twist. We already manipulate space-time just on a tiny scale. Every time we use mass energy, fuel, momentum, electromagnetism, we alter our gravitational field. Imperceptibly, yes, but in principle, it's real. Could future civilizations build devices that channel this effect more powerfully? Maybe. There are speculative designs out there: gravitational field amplifiers, negative mass drives, even dark energy thrusters. Right now they live on paper, but so did rockets once. And then there's the idea of frame dragging, already observed around Earth thanks to the Gravity Probe B experiment. When a massive object spins, it drags space-time along with it. The more massive and faster it spins, the stronger the effect. So a rotating black hole, that's a space-time twister. Some theoretical engineers suggest building ring-shaped spacecrafts that rotate to harness frame dragging and perhaps create local warps. Again, no working model, but it's fun to sketch on napkins. Quirky historical note. In the 1950s, before the math of warp bubbles was even around, there was a real US Air Force project called Project Grudge that speculated on advanced propulsion systems based on manipulating gravity. Most of it ended up in the classified landfill of Cold War speculation, but the seeds of space-time engineering were already sprouting. And let's not forget wormholes again. Those theoretical tunnels through space-time. As we've seen, they require curvature. But unlike warp drives, which push against space, wormholes fold it. If you could stabilize one, you could create a passage between distant regions, or even different times. In this sense, manipulating curvature could mean controlling connectivity, deciding not just where things are, but how space is linked. Engineering reality, not travel. Fringe alert. Some have speculated on using extreme sound waves or high-frequency gravitational waves to affect local space-time. The amplitudes would have to be astronomical, but the dream persists. If we can generate enough focused energy, we might nudge geometry itself. Then there's the big maybe, emergent gravity. Some modern theories suggest space-time isn't fundamental at all. It emerges from quantum information. If that's true, manipulating space-time could be a matter of manipulating information patterns. Code the right structure, and curvature follows. It would be the ultimate programmable universe. Still, we're not there. Right now, our best space-time engineering involves riding on already bent geometry, using gravity assists, plotting orbits, building telescopes that factor in curvature. We don't bend space-time yet, but we respect it. We follow its curves like ancient sailors followed the wind. And maybe that's the point. Before you can reshape the cosmos, you have to learn its language. You drift away from warp bubbles and dream propulsion devices now. The universe swells ahead, still mostly indifferent to your efforts. But in the back of your mind, the question lingers. If space-time can bend, and if that bending can be shaped by energy and mass, then maybe one day we won't just observe the curve, we'll craft it. You glide onward, leaving behind the hypothetical warp coils and exotic energy bubbles. Ahead, the sky darkens, not with emptiness, but with possibility. The air, figuratively speaking, gets thicker, stranger, full of questions that refuse to go away. You've followed the math, chased the equations, tiptoed around black holes and plank walls. Now it's time to step into the less formal neighbourhood, the one with rumours, the one with aliens, conspiracies and curvature-based wildcards. Welcome to the back alley of cosmic speculation. Don't worry, we'll keep it grounded. PG-13, as always. But just because something's fringe doesn't mean it's meaningless. Sometimes, fringe ideas exist because mainstream science hasn't caught up yet. And sometimes, because they're just really good stories. Let's start with a favourite. Do aliens bend space-time better than we can? It's not a silly question. If intelligent life arose before us, and statistically it's hard to argue it hasn't, then they've had a head start. Maybe a few thousand years, maybe a few million. Maybe they learned to manipulate gravity the way we manipulate radio waves. Could they travel by bending space? Maybe they communicate that way. Maybe they don't transmit signals through space. They warp the path between sender and receiver. Instantaneous communication, not by cheating light speed, but by remodeling the distance itself. We've seen no hard proof of such civilizations, no warp bubbles, no glowing gates. But we have seen things we don't fully understand. Gravitational anomalies, fast radio bursts, unexplained lensing events. Are they natural? Almost certainly. But if an advanced species were bending space-time for their own ends, we might see exactly those things. Some have speculated that black holes themselves might be engineered. Maybe not all of them, but perhaps some. If you wanted to store energy on galactic timescales, or encode data in Hawking radiation, or even build a time-looped civilization, a black hole would be your tool of choice. Fringe, yes. But there's precedent. Dyson spheres were once science fiction too. Now they're in SETI search parameters. In that spirit, let's talk about dark flow. Discovered in 2008 and debated ever since. Dark flow is an observed motion of galaxy clusters drifting in one direction, as if being pulled by something beyond the observable universe. A curvature, a mass over density. A bubble universe next door? No one knows. Some physicists say it's a data artifact. Others say we're seeing the gravitational influence of something outside our cosmic horizon. If that's true, then space-time doesn't just curve within our universe. It interacts across boundaries we thought were uncrossable. Now pause a moment. You're floating through a region of space where nothing seems out of place. Stars drift, galaxies spin, gravity hums its usual tune, but underneath it there's this itch, a discomfort, the kind that creeps up when you realise that what we call normal curvature, black holes, expansion, gravitational lensing, might just be one layer of a deeper structure. Let's go full tilt for a moment. What if we're in a simulated universe, and the curvature of space-time is just a rendered effect, a computation happening behind the scenes? Some fringe thinkers have toyed with this, suggesting that quantum fluctuations and discrete curvature steps are signs of underlying code. The pixelated nature of space-time, as hinted at in loop quantum gravity or causal set theory, could be interpreted, very loosely, as a digital framework. One curious historical anecdote. In 2012, a group of physicists proposed that we might detect the limits of simulation by looking for lattice effects in high-energy cosmic rays. If space-time were a grid, there could be directional biases at extreme energies. So far, nothing conclusive, but the fact that it's even publishable says something. Then there's the idea that consciousness and curvature might be linked. Deep, deep fringe. But some researchers have asked whether highly ordered systems like brains could influence local space-time, not gravitationally but informationally. If space-time emerges from information, and consciousness is a form of complex layered information, is there a feedback loop? Could extremely advanced minds alter geometry not by mass but by pattern? Okay, time to back up. Let's steer away from telepathy-powered wormholes, back to solid, weird but mathematically plausible territory. There's also the ER equals EPR conjecture, coined by Leonard Susskind and Juan Maldacena. It proposes that Einstein-Rosen bridges, wormholes, and quantum entanglement, Einstein-Podolsky-Rosen paradox, are two sides of the same coin. In this view, every entangled pair is connected by a microscopic wormhole, not traversable, not useful for travel, but a literal physical curvature link in spacetime. If this is true, then the entire universe might be stitched together by entanglement. The web of quantum connections could define the very geometry of space, which means, again, curvature isn't just caused by energy and mass, it's built from relationships. And maybe, just maybe, advanced civilizations figured that out before us. They might not fly ships across galaxies, they might knit entanglement into knots, forming pathways in the underlying geometry, tunnels of trust, corridors of causality, portals not through space, but through quantum-linked curvature. It's possible, of course, that we're just romanticizing ignorance, filling in the blanks with dream-shaped glue. Most of what we call anomalies today will be mundane tomorrow. But sometimes we find out the fringe was right all along, so you keep floating through the lensing halos and silent quasars, past the warped echoes of fast-moving galaxies, past whispered rumours of bent geometry and impossible civilizations. Because even if the universe isn't full of aliens sculpting wormholes, or dark flows from adjacent cosmoses, or space-time knitting itself from thought and entanglement, even if it's just mass and energy, doing what mass and energy do, that's still the most incredible magic you'll ever witness, because curvature, even the boring kind, is the universe expressing itself, shaping itself, and hiding secrets in the folds. So keep looking. There's more curve where that came from. You've drifted through every scale, every fold, every whispering loop of space-time, from the yawning mouths of black holes to the jittery tremble of quantum foam, from the earliest inflationary pulse to the cold stretch of dark energy's quiet tug. You've asked whether space-time can bend forever, whether it can break, and whether we can shape it with mind, machine, or madness. Now here, in this last stretch of curved quiet, you circle back to the deepest question of all. Why does space-time bend at all? Why does mass curve geometry? Why does light follow these curves like a leaf caught in a stream? Why not a straight universe, stiff and static, unmoved by stars and galaxies? To answer that, you have to zoom in again, not to the Planck scale this time, but to the logic behind the universe, the framework that lets bending happen in the first place. Einstein didn't invent curvature, he revealed it. Before him, Newton saw gravity as a force, instantaneous, action at a distance, like invisible strings pulling masses together. But this view had cracks. It worked for apples, it worked for planets, but it couldn't explain light's path, or gravity's influence across vast distances without violating the speed of causality. Einstein's genius wasn't just math, it was insight. That mass doesn't pull, it tells space how to bend, and in turn, curved space tells matter how to move. No invisible strings, just geometry doing geometry things, and from that flowed everything. Orbits, tides, lensing, expansion, black holes, gravitational waves, a universe that moves not through force, but through shape. It's a subtle shift, but it changes everything. Forces are pushy, they act on things. Geometry, it just is. That's why you can think of the universe less as a machine and more as a stage, where events don't unfold because something forces them to, but because that's how the structure of space demands they move. Historians still argue whether Einstein's equations are the final say, or just the first good draft. But what they gave us was a way to see curvature not as an anomaly, but as the natural state of things in the presence of energy. Curvature is reality's way of expressing itself. Mass, motion, pressure, they don't just exist in space, they define it. So why does it bend? because bending is how the universe knows what to do next. The deeper answer might come from something even more abstract: symmetry. In physics, symmetries are rules that say, if I rotate this or shift that, the laws of nature still hold. And when those symmetries break, or when they apply in non-obvious ways, they give rise to forces. Gravity itself, in one view, emerges from a gauge symmetry, a mathematical invariance of how geometry works. Some cutting-edge theories even suggest that gravity is entropic, that it arises not from a fundamental interaction, but from the universe's tendency to maximize disorder. In that view, curvature is not just response, it's thermodynamic necessity. And if that's true, then you've been asking the wrong question all along. Not, how much can space-time bend? But, how much does it need to keep the story going? Curvature becomes not a limitation, but a conversation between energy and entropy, between motion and information. You begin to realize there may not be a fixed limit to how much space-time can bend in the traditional sense. There may be practical limits, yes, energy constraints, quantum thresholds, boundaries of measurement, but space-time in its purest form can bend however the universe needs it to, sharp as a singularity, soft as a lensing halo, subtle as the drift of time on GPS satellites. There's one final whisper from the math, and it's this: curvature is always relative. Relative to mass, relative to scale, relative to your path through it. You can walk across a field and call it flat, but an ant sees hills, a molecule sees mountains, a photon riding a geodesic sees only its destiny. The more you look, the more you realize that space-time is never perfectly flat. Somewhere, someone is always bending it. You included. You, with your mass, your motion, your presence. You curve space. Maybe not a lot, maybe not in dramatic cinematic ways, but you're part of the equation, part of the dance. Your atoms weigh something, and that weight bends reality. So here you are, suspended at the end of a long journey through space-time's folds, no longer asking if it can bend or break or wrap around itself like origami. Now, you just float in the truth that space-time is alive with possibility, that every star curves it, that every moment spins it, that every breath you take reshapes it, just a little. So no, maybe there is no final number, no hard cap, no moment where the fabric gives up and says, no more. But there is structure, there is rhythm, there is a whisper in the curvature that says, I'm holding the shape of everything you've ever known. And when you listen closely, you can hear it bend. Now let it fade. Let the bends and warps, the foamy edges and star-pulled curves begin to ease. The equations dissolve. The theories drift like ash on cosmic wind. You've run your hands along the folds of reality itself, felt the flex, seen the deep swirl. No need to chase the singularities anymore. They'll be there tomorrow, waiting at the edge of thought. Tonight, the universe holds you gently, in a curve so wide, so slow, it feels like stillness. Let your breath fall into rhythm with space. Let your thoughts soften. You've asked big questions, and for now they can rest unanswered. Because even unbent, the fabric cradles you, and somewhere far away a star curves the void. Sweet dreams.